is, it wasn't there, it's along here. Well, there it is. So the only thing that happens different in these is that it's a combination of stuff, all chapter 12 and wait a minute, let me check something else. Is it working? Oh, it is working. Well, that's weird. Uh-oh. So that kind of means the last lecture might not have been. Oh, well. So the last section, 12 and then 16, chapters 12 and then 16, we're dealing primarily with finding the acceleration. So now all we're going to do is we're going to multiply times the mass and figure out the forces out of it. And it sounds simple, although there's some difficulty to it. We started in the other class, we talked about this. This is nothing more than, let's say you're looking at a 100-kilogram object, and then you grab these, then that's G. So F is equal to, or weight is equal to mg. So, the mass of each part. One of them is going to be the mass of the Earth, the gravitational constant, and how far you are from the center of the Earth. So, and I don't know how far that is, actually. Yeah, I mean, if you moved up to Denver or up to Pikes Peak or something like that, the gravitational pull is less there because you're further away. But I don't know the... Yeah. Here, let's just check. Let's just say 3,000 miles. Wow. That's the radius? That's a big planet. So it still adjusts a little bit, but you percentage-wise, you move to Denver, that's only an extra 1,3960 compared to, and then I guess you go to Pikes Peak, that's another 2. So you will find a different gravitational constant there, but it didn't change the mass of the Earth. Let's see, does he have the mass? There's your mass of the Earth. Look at that. You know what? Let's see. What is his units over here? I know I'm distracting. I mean, this is going to be distracting. Oh, look at that. Okay, let's just try something. Just out of curiosity. Here. I know I shouldn't be doing this, but this is just part of who. Oh, no. Did I do the wrong one? No, I did the right one. I've got to do this now. This is just, or it's just not. I got to. The other thing, that's the miles. What is there's the mass. Okay. So the mass of the Earth is M is equal to 5.972. And this is very stupid. E to the 24. Okay. There's the mass of the Earth, right? E to the 24, right? Now, let's see. How many meters is 3,000 miles? Yeah, let's just, well, here. I forgot the number again. 3,959 miles. It's a big planet. In meters. Miles to feet. Wait. Oh, okay. Okay, so 3,959. Okay, look at that. Okay, so I'm gonna take that meters. Okay, so this would be R is equal to that. This is gonna be weird. I just have to do. I'm sorry. I just got to do this just because I just want to see if I know what's going on. So G is this big G is equal to 66.73 e to the minus 12, right? Now, if I had M, right? Did I have it as M? I did. M times G divided by R divided by R. I'll be dang. Look at that. So not only is it 9.81, it's 9.8168. We've been wrong all along. And let's see, what would happen if I moved it? Okay, now wait a minute. If I move to the top, and I know this is just ridiculous that I'm doing this, but here, let's say we moved 3 miles up. So here, like, well, Pikes Peak is like, it is almost 3 miles, I think, from sea level. It's 14,000. I think it's 15,000 feet. So it's about 3 miles. So let's say 4,800 meters. What is G up there? So let's see. R, I'll do it this way. R plus 4,800 extra meters, square it. What's G up there?
You're going to be satisfied with your answer. It wasn't exactly 48.
Oh, it wasn't? Well, it's good enough. So it's about 9.8 up there. So let's see. 100 pounds object down here. This is ridiculous. Why am I doing this? But I've got to do it now. Yeah. So here it is. Okay, so we'll say this is D sea level. And we'll say this is G Pikes Peak. So now G Pikes Peak divided by G sea level times, say, 100-pound object. Oh, geez, not that much. That's why I didn't feel like I was floating around when I was up there. Okay, so it's not a whole lot. So, okay, never mind that.
I mean, you would almost feel a pound lighter.
Yeah, probably. Yeah, because if you were like me, I'm like, oh, I'm not 1,200 pounds. Well, yeah, a pound, yeah. Yeah. Okay, well, there you go. So, the complete diversion.
The complete diversion would be to find out how much you weigh up in.
Well, there I'd have to find the radius and then the mass. But you know what? He did tell me the sun. If I was standing on the sun, let's say I had asbestos suit. Wow. Oh my. Pretty big mass. We'll figure it out later. Anyway, now I'm completely distracted. There you go. So, in other words, that is the G, obviously, because we figured that out. See, you learned something the other class didn't know. Why don't you go rub their nose in it? Okay, so so here you go. Oh, G is equal to GME over R squared. He did that for us. Look, okay, so he did all that. And so here is his G. And the other unit's 32.2. The only difference is here in this course as compared to physics is that the you know, over there you saw force equal mass times acceleration, but now we're in statics and dynamics. So before you had sum of the force equals 0, but now you got the left end behaves just the same way. You do a free body diagram on, now this is stupid, it's a marble or something, but you could have a force here and a force there. They go together to create a force there, meaning this has to go the way the resultant force is going. So if I pulled it this way and that way, it's going to go this way. So the acceleration is going to go that way. So on the left, you do a free body diagram. On the right, you don't do much. I mean, you could show this arrow if you wanted to, and it would match this arrow. The scaling factor is m. So that's pretty much it. And then the key is, what does this thing look like? Well, if you go down, okay, so he goes down. Okay, there's a guy. He's being pulled on. Look at his face. And then he's being stopped. Okay, so here he's talking about equation motion for system of particles. The only system of particles we've got, which means you've got two masses somehow connected together, they're always connected through a pulley or a rope. So, but he makes it general. But in effect, if these were connected to each other through a rope, there would be a relationship between the accelerations. And we'll look at that later. So here, then he breaks it into rectangular coordinates along the X, along the Y, and along the Z. They have to match each other. And then he starts, does he do a problem yet? Where's his first problem? Okay, he also breaks off and says, okay, this is something I talked about, and then I had to backtrack. Okay, so he talks about the acceleration is a function. If it's a function of time, you've got to use these to integrate. And then I said something that was incorrect. I said, you know, if there's a force pulling on an object, and usually it is a constant force in our book, but it turns out it isn't. They have other problems. If it is a constant, then you can use those constant relationships. If not, you got to use those. So I immediately said, oh, they're all constant. Well, that's not true, because then 2 problems later, there was one he had in an example where it wasn't constant. And so if you go through this, here's what you do. You start with this. Okay, yeah, you got a block. Somebody's pulling it with 400 newtons. It has a coefficient of kinetic friction is this 0.3 sitting right here. Then the first thing you do is you draw a free body diagram. And you notice what he's done is he's done his free body diagram, and then he did his right-hand side. So his right-hand side, he had an A component that way. He had no acceleration in the Y. So the block's not coming off the ground. It's only going to the right. And then what he did is he said, well, I have a component going this way. I have a component going that way. And this is what? The 400 cosine 30. And this is the 400 sine of 30. And then what he did is he said, well, let's do the X first. So I'm going to do this one, do that one. I don't have any more. So I do that one, pulling it to the right. This one's slowing it down. And of course, here he had his normal NC, and he wrote this down. Turns out it's 490, but you're also pulling it up. So on the Y, he had the normal force pushing on the bottom of the box. The 490, which is the, 50 kilograms times 9.81. And then the 400 pulling it up, sine of 30, which is pulling it up, tells you what NC is. This bottom one tells you it's 290. Then you take that 290, shove it right there, and you get the acceleration. Now, since every single time in the future, the 400 pounds is there, so in other words, this 400 newtons is fixed and doesn't change, and none of the forces over here change, then it is a constant acceleration. And that's where I made the mistake. I said, oh, all of them are constant in the book. No, they're not. So in that case, you can use this. And you can find out, oh, the velocity is 15.6 at 3 seconds. You could have also added something more to the problem. And I went ahead and did that in the other class. And that's this. You could say, how far did it move? X is equal to x naught plus Vx naught, the initial speed, plus this time the acceleration in the x constant t squared over 2. This is if you have a constant acceleration. Turns out that his initial velocity both ways is 0. And so if you just move this over and say delta x, or the amount that it changed, would be AXC, which is this number, times t squared, which is 3, over 2, or it would have been 5.185 times 3 squared over 2. That would have been how far it would have moved. So the fact that you've got a constant acceleration means you can use these equations like that. And then I was all happy that I've spotted it and watched what happens next. Okay, so then I go through the lecture and I'm like, yeah, and I didn't feel like looking at that one. Then I came back and I was like, oh, I'll come back to this one. Come down here. Wait, was it that one? That was it. That was it. Yeah. So then the next thing that happens, what does he do? He says, I have a non-constant force. And so that messed with me. So I was like, wait a minute. Okay, so if I've got this that's equal to 40t, then I have sum of the forces in the x equal mass times acceleration in the x. Then I just have, and say this is the x direction, then I just have 40t equal to the mass of all this junk, which is 900 plus 550 plus 325, all that added up, divided by 32.2, times the acceleration. So now I've got this silly equation. So now I've got the acceleration equaling to a constant times t, which the constant is that 40 divided by this mess. And so just like that, I had to eat my words. And sure enough, that's what he does. He ends up with 40t is equal to 900, 550, 325 divided by 32.2. You get that number. And what do you have to do then in order to find things? The force. So in other words, the force is doing like this. So here's your force. Here's time. It's just going like that. It's constantly increasing. So your acceleration's constantly increasing. So since that's the case, you got to use these. And so you integrate. So what you had is dv dt is equal to acceleration. We take the dt on the bottom, you put over here, you put it right there, and you leave the dv over here. Then you integrate. At 0 seconds, the velocity is 0. At 2 seconds, we want to know what it is. And so we put v is equal to this, take the derivative, put that in, you got 1.45 seconds. Then he wants to know what's the tension in the cable of the first car. And so what he does is he takes this thing, he does the free body diagram on it, and he says, okay, that's still that 40t. This is the tension, and this is the mass, and there's my acceleration, and there's my 2 there as well. So then you move this over, and you get the tension at that point. Now, you could have done the other way. You could have done the back end. You could have done the free body diagram on the back end and said the tension is creating that, but this is, in other words, let's see if we get the same answer. Okay, so if I do that, oh, here we go. Try to obtain this same result by considering the free body diagram on carts B and C as a single system. Let's try that. So here's what I'm going to do. I'm going to say, use this little snippet thing and do like this. Oh, come on. Just snip the thing right here and then go over here. Okay. So, oh, here's I was messing with the okay, now free body diagram, those two are in there, but I also have the tension. So sum of the forces in the x equal mass times acceleration. But this time the mass is 550 plus 325 over 32.2. And the acceleration was that funny number. What was it? Okay. Here it is. 0.7256 t. 0.7256 t equal to tension. There's nothing else over there. So let's see if I get the same thing. Oh, and it's at 2 seconds, right? Okay, so I might be able to do this. But it might be above my pay grade. Okay. Clear the screen. Okay. 50, 325 divided by 32.2 times 0.7256 times 2. 39.43, or almost 40, but 39.43. So I get 39.43. Is that what he got? 39.4. Okay. No, it has to be the same. Yeah. Now you could do this. What's the tension in the back one? What do you think the tension in the back one is? So you could do this. I'm gonna do the tension in the back rope. So it's a different tension than the front rope. Well, okay, so this time it's like a T2. Okay, so here, sum of the forces in the X equal mass times the acceleration. The mass changed. And so T2 is equal to 325 over 32.2, 0.7256 times 2. And so what would that be? You just take off that 500 and you get 14.64, or about 14.65. So it's a little bit less there. Well, think about it like this. Okay, so let's imagine the weird scenario. Imagine all the weight, instead of 325, this was, all of that was transferred here, and this was only like 2 pounds. So it was accelerating the same amount. So you just have an object, say it's 32 pounds.
Well,
So,
I mean, so I can imagine, like, if I've got 500 pounds on this side pulling me this way, I'm only 10 pounds pulling me this way. I understand it.
yeah. But what's going to happen? Yeah, what'll happen is if it's doing that, it's going to, the sum is going to pull you one way.
Why does it not happen? Why does it happen to me?
Because you have mass. So it's pulling
What if
you.
it was like a 500-pound rope?
Well, now if it's a heavy rope, it's going to be, you're going to have to slice it somewhere and do a free body diagram wherever you slice it. And so actually, huh? It will change down the rope, believe it or not. If you had like a chain, like a really heavy chain, yeah, it would change the tension in the chain. If the chain was really heavy, would change as you move down the chain. It's kind of hard to say. Say it's just a heavy rope, yeah. So yeah, it would. It's weird, but that sort of puts you. And then I asked him this question.
Wait, so you've seen those videos where the hydraulic press pushes down a bunch of paper? It doesn't can't get through it. There's so much paper.
Okay.
That kind of the same thing, because you can't get through it because there's a lot of mass. So there's a lot on the top, but nothing on the bottom. There's so much there. So the amount of force that dissipates when you get to the bottom. You see on the top a bunch of it curves in, but then it gets.
Oh, okay. So you're talking about trying to knife edge?
It's kind of like the same as like in the road.
it's the same thing. I see what you're talking about. I didn't understand what you were relating it to.
Oh, okay. Well, so if you're good with it, I'm not quite.
Hydraulic press is going down on the paper.
Okay.
It's like the top of it. gets
Oh,
pressed in.
yeah. And you're
So when
saying,
you flip this out, it's kind of like the same as the rope, where it's like all of the force here and it just kind of.
oh, okay.
The force has to stretch the rope out.
Yeah.
So that's where your force goes.
But not if it's really small.
Okay. So I think what you're,
That's why we have one piece of paper.
Not as much force required.
and I'm thinking maybe you're thinking also of deflection too. Are you thinking of deflections? Because as the hydraulic press came on this set of paper, is the paper kind of deflecting?
Yes.
Okay, so that's not exactly the same, but it's a similar concept in one way. That imagine you had a real soft eraser. You put a pencil on it, you could just shove a hole right in it and pick up the. But if you put the same amount of weight and put it on just that one spot, and like the whole your fist, and put the same amount of force on it, it's
Isn't that kind of similar? Because if you're pulling on the rope, this one's got 4 on it. There's going to be a lot more. I just thinking.
Well, that's a good way.
That'll be a thing that I'll be like, oh, I rushed on it. Huh? That was the acceleration of pound.
Yeah, that was he did that. Yeah, that's where he got that one from.
Yeah, but then also be your acceleration. I guess not because it's not in the Y direction.
Yeah.
So all of the objects, the front car, the middle car, and the back car, have the same acceleration. If they don't, they're going to be coming apart.
Yeah, it's F equals M G.
And let's see, the next thing I did is I went into this and I told them, I said, you're lucky this one has a smooth collar, because if it didn't have a smooth collar, it would be awful. And the problem here is if you really look at this, you do the free body diagram, the force, the direction of this force and the theta is a function of y, if you really think about it. So the Fs, force due to the spring, is a function of theta, which is a function of y. Oh, y'all are still thinking about that?
Like, makes sense. Like, in the case here, the stress.
It's a spring stiffness is what it is, kind of. So as you push on an object.
It's not uniform throughout the whole point, right?
Oh.
It makes sense that I knew the answer.
Oh, okay. So in this case, what he does first, he breaks it apart at a certain theta. And then what he does is he creates the two equations based upon that. But he doesn't address this quite yet, that the force of the spring, the direction, and the part that goes in the X and the part that goes in the Y is a function of theta, which is a function of Y. So that makes it kind of difficult. It'd be worse if you had a non-smooth collar or a friction in there. Turns out you can go in and do Fs and have this actual value. That's great. That gives you the magnitude as a function of y, but the direction comes from trig. And then you take this component and this one and put it back in these two to get the compressive load, or not the normal load on the collar, and then the acceleration at that point. And this one, it's hard. Okay, so if you were sitting there looking at this, it's hard now to go and find like, okay, yeah, this is the acceleration. It's a number, and it's at that angle, and it's at this y. That's great. The problem is it's also the acceleration is a function of theta, which is also a function of that, of y, which means you can't, it's not constant. You can't use those relationships. So if you were going to do that in general, you'd find it would be a reasonably annoying nightmare, in that instead of putting in 1 meter right here, you would leave it, you would leave that. And if you were going to solve those equations out, you would have to have some integrals to go through, like to find the acceleration as a function of y. Now, if you had that, you could come up and you could find the velocity as a function of y. That is very difficult here using these methods. But it turns out in energy methods, that's very easy, because what you do is, you 1/2 k delta squared, 1/2 mv squared, and what's the other, mgh. And if you didn't have any losses, you would just use those 3 energy terms and you would exchange energy back and forth. Believe it or not, you just pop out the velocity just like that. So in these problems like this, very, very complicated, in energy methods, if you were asked to find the velocity, it would be very complicated. If you were asked to find the velocity in energy methods, very, very simple. And so that's why I like chapter 14 a lot, because what initially was an incredibly, incredibly difficult problem is now very, very simple with energy methods. So, and that's a chapter for later. And then let's see, what else did I do? I went in here. Oh, and the last thing I did, okay, did I go? Okay, I got far enough along to. So the last thing I talked about was this. Okay, before you had, okay, think about it. I had 1 particle, 1 sleeve, collar, whatever you want to call it. Here I had a cart, but I also had 3 other carts. They were connected together with a tension. Here I had a cannonball, which I didn't even look at that one. I had 1 object here. Now you're looking at multiple objects, multiple particles. So what you have to do is you have to do a free body diagram on one of them, block A, then block B. So you have 2 individual equations. But it turns out that because of the length of the rope having this relationship, and I always include that delta, you take 2 derivatives of it, and now you've got the acceleration of one of these rope blocks is related to the other. So somehow the acceleration of A and B are functionally related through that rope. Unless, like you say, the rope is like a spring and it stretches, and we don't even want to think about that. So what you find out is this: the acceleration of A, well, twice the acceleration of A is the acceleration of B in the opposite direction. And so then you can take this equation, and this equation, patch them all together. You got 3 equations and 3 unknowns, and there's your 3 unknowns, and you solve the 3 unknowns. So the only way this works is if there's a way to relate the accelerations to each other, and that's what the rope equation does. Without that, you can't solve them. I mean, if you have 2 individual particles that are moving around on Earth and they're not bound by a spring or they're not connected by a rope, they're essentially 2 individual unrelated problems. But the rope makes them, ties them together and says, well, the acceleration of this is 3 times the acceleration. In this case, it's twice the acceleration of that one. And then that's where these rope equations work. Yeah. It gives them a relationship, kind of, so to speak. So we can't get away with the rope equation, without the rope equation, the length of the rope kind of thing, especially if there is a rope. And then what's funny is, okay, in that other class I said, okay, if you think about it, in chapter 12 we had started with acceleration. We monkeyed around for a while with it. Then we did projectiles. Then we did the v squared over r. Then we did the polar or, and he calls it cylindrical coordinates. Then we did the rope, and then we did these relative velocities. It turns out there, with the projectile motion, there's nothing to do in chapter 13 on it. There's no projectile motion. So you go through the set of problems, you see a bunch of masses all being pulled around, doing things like this. Okay, here's two masses being pulled. They're related to each other. You get all this sort of stuff. Then what happens to you eventually? Okay, there's a lot of problems, it looks like. Tons of problems. Speak of the devil, I messed up. So there must be, he's got a force is equal K times velocity. Projectile motion in the ocean. That's weird. Okay, so there, I ate my words again. Then he goes into normal and tangential. Okay, so you find the acceleration tangential, normal, v squared over r. For example, you come down a ski slope and you do like this. How much are your legs going to have to hold up? Well, your mass, acceleration, your weight, you do a free body diagram. So here is an example where the car is going around in a circle, and he has this type of information. You can figure out, because he's going in a circle, and he must define rho somewhere. Okay, now I guess this is a standard. Okay, so here's one where the rho is 1 meter. Free body diagram, you can work it out. Here's a skier, and he's got that. You figure out your rho, 100 foot, and then turns out you use that rho. There's your mass. There's your free body diagram. On the left, your weight, and then the NA. So what did he weigh? 150-pound skier is about to leap off at A. What's the extra weight? So you got all this. That's all fine. And then you have one more section after a whole pile of other problems. Okay. Cylindrical coordinates. Now here he has a funny thing, a really weird relationship. We'll talk about it a little bit, but it turns out he's okay. He does okay with it, but I like to think of it a little bit different. And that is that the tangent, and he is doing that, but he's defining some other things. And that is, if you come back to the tangent of a path is always in the same direction of the velocity, then that helps you understand this stuff. So I don't know that he adequately says that, but he comes in and finds all these funny little angles and DRs and stuff, and it'll drive you crazy a little bit. But he does use them some. And if I make you use them, it's going to be in a take-home part. So the same thing comes up. You find your R dot, R double dot. He gave you the theta and the theta double dot. Here's your theta dot is 3. It rotates with a constant angular velocity of 3, which means theta double dot 0. That way you can figure up all your accelerations. So you get your acceleration, radial acceleration minus 10. Wow, that's weird. Theta acceleration, the same value. And then you substitute the theta and the R back in here. Theta and R right back in here. So what you're doing is you're doing a free body diagram off of an object. You break it apart. You're left with AR and A theta. Then you're back to doing what you were doing in chapter 12. You're doing this mess where you're just inserting it. You're getting your two numbers. This usually doesn't turn out to be that, the same values, but I think in this case, maybe he shouldn't have done that, because more times than not, they're not the same value. It's just odd. So, but then you put them back in here. You take this one, put it in here, take the other one, put it in there. Then you have enough. You can find NC from moving this over. And then once you find NC, you put it in here, and you can find the F out of that. And so all you're doing, in addition to what you did in chapter 12, which is all this junk, now you're coming back and you're saying, I'm going to draw a free body diagram, making sure that I point one of them in the R direction and the other one in the theta direction. And that's all you're doing. So you're adding this and this to the last chapter. And that's it. Now, some of them will twist your head a little bit. Look at that. He says the F, the normal is 7.2 newtons. The F is nothing. So where's his F? Oh, here's his F. So at that particular instance, it's nothing. That doesn't mean it's nothing, a little bit further down the path. I mean, already you can see a problem here. If you move it to the point where it's perfectly vertical, that's just not possible. So you're going to find a huge F, and it's not going to go anywhere. Plus, you won't be able to maintain your theta dot equal 3. So here's another one. Looks like he has a roller on the ground, and this thing is spinning around. Theta 0.5, theta at 60. Wants to know at 60. Okay, smooth cylinder passes through the slot AO, which is a little slot. You can kind of see it a little bit. If the arm is forced to rotate in the vertical plane, meaning it's just rotating like this, a constant rate of that, determine the force that the arm exerts on the peg. And so here you're basically zooming in kind of, although he didn't zoom in a whole lot there. The ground is shoving up on this cylinder. The cylinder has a little bit of weight. So the biggest key in these things is that free body diagram, getting that part right. The other part, you can just plug and chug. This one you have to kind of look at and think about, because he could have all sorts of things. So all along, he labeled this pushing up on this cylinder. He has the cylinder weighing this. And so technically, he should erase this blue sleeve and say, this is the force that the blue sleeve is pushing on this thing to make it head off to the right. Does that make sense? So this part, blue, should not be there. Depends on your perspective. So the FP is caused by the blue thing. So he has AR, and he goes through and figures that out. And then the A theta goes through and figures that out. But then he's going to have, and this looks awful already. I didn't even see that part to the left. So he takes that diagram and he says, hey, I'm just going to plug and chug it. I got to make sure my angles. And so notice what he does. He does it in the R direction, just kind of up and down here. And then in the theta, because you need to match those. You need to match those because you're going to get that number and you're going to get that number. So you have to match the R and the theta. He does this. He breaks that 19 into sine. And then he does, NC into the sine. And then the theta, this is the theta. So it's the cosine here and the cosine to bring you there. And then this FP. And that's the theta and that's the R. So from figuring, you can relate theta to the, so he does this, I can see that already. And then this is really nasty. So take the derivative of the cosecant, and then it goes, blah, 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 blah. He comes up with these three, which these are okay, because he told you these. This is awful. He gets that, then does to do it again. Then he's got to put in the theta and get that. And then he has to, so once he has those, comes down, he has the numbers, the 5 numbers. So you'll want to know theta dot theta, R dot R double dot. You really need to know theta in order to figure out what these are, because he had to have theta is equal to 60 to shove in here, and then to shove in there, and then to shove in there. And that gives you this. But you don't need the theta in these. And so then you just go, okay, that number goes here, minus this number goes here, that number goes here, and then you just fill it out. So you get an acceleration and acceleration. Then you go back to the equation up here and shove this one in that one and shove that one in the other one. When you do that, and he he doesn't do that specifically, but when you do that, all you're doing is you're just taking these two, shoving them in here. Now you'll have a number and a number, and you can move stuff over. You've already got theta is 60, so you can put in 60, 60, 60, 60, shove it over and find NC, which, here it is. And then from the NC, you shove the NC in here and move everything over and find the FP. And so that's that. So you'll find this one first, then that one. So really the only thing you added to, you got this same crap again. That just, this part to here is that same stuff. You still embed, you only have this added. So now that you got these two numbers before you thought you were done, you are done, but now you take those and shove them back in there and you can find the force.
The only thing we're really adding is the F equals M over the
Right. That's it. That's all there really is. Okay, so I kept you too long. Okay, so then after you do it, guess what? There's nothing else. There's no more.